The laboratories of chemistry and radiation chemistry are devoted to basic and applied research in the field of nuclear engineering, medical application, and material science. Within radiochemistry, our research focuses on the areas of radioanalytical chemistry, nuclear fuel cycle, generation for reactors, and nuclear decommissioning and waste management. As concerns radiation chemistry, the research activities are related to the radiation-induced modifications on materials that have undergone high radiation fields, such as those used in nuclear, technological, or medical applications. Let's start to see some of the activities we do in the lab. For example, in the framework of nuclear safeguards, it's often asked to determine the concentration of uranium. As you know, uranium is present everywhere in nature, in rocks, in water, in living organisms. Besides isotope artificially produced, uranium naturally exists as uranium-248, the most abundant isotope, uranium-245, and uranium-244 as traces. Since they are all alpha-emitting radionuclides, they can be measured by a radiometric method, such as alpha spectrometry, after a proper sample manipulation. This technique allows to quantitatively measure their concentration down to about 10 to the minus 3 becquerel per gram. In the case of a water sample, a representative sample of water is taken, acidified by the addition of nitric acid and added by a suitable tracer, usually uranium-242, with known activity to monitor uranium chemical recovery. Uranium is concentrated by a co-precipitation method, and the so obtained precipitate subsequently dissolved by concentrated nitric acid. The so obtained sample solution is loaded on a column specifically designed for uranium separation. The resin inside the column is preconditioned by adding 3 molar nitric acid. In this environment, indeed, uranium is retained by the resin, while interfering radionuclides are removed. By changing from the nitric to the chloride medium, uranium could be recovered by adding 1 molar hydrochloric acid. At this point, the sample solution has to be prepared for uranium measurement by alpha spectrometry. This is done by electrodeposition. This step, which requires about 2 hours, consists in electrolytic deposition of uranium onto stainless steel planchets. For quantifying the uranium concentration, it is necessary to calibrate the alpha spectrometer by a suitable calibration source, evaluate the counting efficiency, and register the background in the region of interest. The sample planchet is put inside the spectrometer cell and the measurement starts. The measurements should last enough time to obtain good statistics. The count registered for uranium-242 enables to calculate the chemical recovery yields. That means how much of the initial uranium-242 and thus of the uranium in the sample has been recovered. The counts collected in the region of interest for each uranium isotope, together with counting efficiency, chemical yield, and background, enables to quantify the uranium-248 and 245 concentration in the sample. As we have seen, the determination of uranium in water by alpha spectrometry is quite difficult and time-consuming, even more in solid matrices. However, it could be performed also by mass spectrometry after a simpler sample preparation. But there is another advantage in using this technique. Indeed, in the case of elements of high atomic number and not very widespread in nature, the mass spectrometer is able to reach limits of quantification in solution of the order of parts per trillion or even lower, corresponding to about 10 to the minus 8 becquerel per gram. In this case, the water sample has to be properly diluted by means of ultra-pure water, with 1 or 2% of ultra-pure nitric acid. To be accurate, dilution operation could be done by weighing the sample aliquot and final diluted solutions. The inductively coupled plasma mass spectrometer available in the lab enables to analyze a liquid sample by nebulizing it in a spray chamber. The atoms and molecules are ionized by the inductively coupled plasma torch. The ions are extracted and focused by ion optic guide under vacuum, then separated according to mass to charge ratio by the quadruple under high vacuum, and finally detected by discrete dynode electron multiplier. The instrument has to be properly calibrated by certified standard solution, and it enables to calculate the calibration line, from which the limit of detection and the limit of quantification can be derived. The first one represents the value above which the presence of the element could be discriminated by that background, while the second one, the value above which the element concentration could be quantified. The same water sample is analyzed in few minutes and the uranium concentration is determined, together with its isotopic ratio. These give you just an idea of what we usually do in radiochemistry and radiation chemistry laboratories, but to learn more, come to see by yourself.